So here we're going to find the volume of the solid about the y-axis bounded by y equals square root x, y equal 2, and x equals 0. So the first thing that I want to do is I want to graph each of these equations, see what's going on here. Okay, so y equal to square root of x starts at the origin and shoots out like this. Okay, y equal to 2 is a horizontal line. I go up 1, 2, and so it looks like this. All right, so that's y equal to 2. This is y equal to square root of x. And then x equals 0. It's here, x equals 0. That's the y-axis. This is the region that's bounded here. It's this region right there. All right. And what are we doing? We're rotating the solid about the y-axis. So the axis of rotation is the y-axis. Okay. And remember, when we're rotating about the y-axis with the disc or washer method, we have to be perpendicular. The rectangles have to be perpendicular, right? So I need my rectangles to be perpendicular, which tells me that these rectangles are in terms of y. So this is a dy for this particular problem. Okay, so once again, for you art lovers, the 3D version of what this geometric shape looks like, well, it comes down like this, and it comes to a point, and then if you spin it about this axis, what's going to happen? Well, it's going to spin all the way around, right? So it's going to kind of be like a top, okay? Or like a tornado kind of thing going on. So this is the Clark tornado, right? Okay, so I know the jokes only get better because they can't get any worse. Okay, so got your little top thing going on here. Maybe, I don't know, whatever. Something similar to this here. Okay, so that's your little 3D representation of that solid that we're trying to find. Now, if I take out one cross section here, you can see that the cross sections are clearly disc. We don't have a hole in the middle, so we're not dealing with the washer situation where we need 2 radii. Okay, we've only looking to figure out 1 radius. Okay, so we only need 1 radius. So this is pi r squared h, right? And the thickness for each of these is actually dy. The pi stays the same, and I need some function of the radius in terms of y. Okay, so that's what I'm looking for now. So that's the game plan. How do I find this distance in terms of y? Well, right now, it's a function of x, okay? But what can I do to rewrite y equals the square root of x as a function of y? I need to solve for x. So to do that, I'm going to square both sides. And so I have y squared equals x. So now my function, x as a function of y, is equal to y squared, okay? So kind of a weird notation. I won't jump into that right away, but that's kind of what's going on there. Okay, so maybe you've seen the function notation like this before. Okay, so I just literally flipped around the roles there. So in case that scared you, I wanted to get rid of that. Okay, so commercial over, right? All right, so that's my dy, right? The width of each little disk in there. Okay. I want to figure out the volume. So I'm going to sum up all the disk from where to where. Well, starting at what? Y equals 0 and working my way up to y equal to 2. So I'm going to sum up all those rectangles from 0 to 2. So how do I write that? Integral 0 to 2. Okay. And then what's the volume for one of those pieces? It's pi times something squared dy. Now, what is the distance? How do I find it? Remember, it's right minus left, okay? Not top minus bottom, because that would be a parallel rectangle. So right minus left. Well, what is the right one? The right one is x equal to y squared. So right is y squared. Now minus left, what is the left? It's x equal to 0. So the left is just 0. So what does this become? It becomes integral 0 to 2 pi times y squared squared dy. Yep, I square a square. What do I do with power to a power? I multiply the exponents. So I'm going to pull the pi out, 0 to 2, and that's y to the 4th dy. Okay? If I integrate, that's y to the 5th over 5 times pi, integral from 0 to 2. So that's pi over 5, 2 to the 5th, minus pi over 5, 0 to the 5th. So the second part goes to 0, 2 to the 5th is 32, so it's 32 pi over 5 is my answer here. Approximate answer is 20.106. Okay. The next problem I want you to find, so kind of, just to summarize, this weird looking tornado has a volume of 32 pi over 5. Kind of a beautiful thing that something so weird has such a simplistic answer. Okay? Find the volume of the solid formed by revolving the bounded region y equals 2 minus x squared and y equals 1 about the line y equal to 1. Holy smokes. So up to this point, we have been revolving about axes, okay? So now we're changing gears and we are going to revolve about a particular line, okay? So we're going to revolve about a particular line. But before we get to that problem, okay? Actually, yeah, we'll go ahead and we'll do this problem. It'll be fine. All right, so let's go ahead and we'll try to work through this problem. Okay, so find the volume formed by revolving the bounded region. So 2 minus x squared, so that's a negative 1 in front of the squared term, makes it a sad parabola. Shift it up 2 units. So 1, 2. And so then, it's going to come down like this. And y equal 1 is a horizontal line here. Y equal to 1. But what is different here? What's going on that's different? Now, like we did in a previous problem where we rotated it about the x-axis and we had that hole in the middle. Remember that problem? Okay. Now instead we're going to rotate it about the line y equal to 1. Okay, so y equal to 1 is the line we're going to rotate this bounded region right here about. So what does that look like in 3D? Instead of being a washer, it's actually going to end up being, well, we rotated it about, it would kind of come around on itself, right? So it ends up just being a solid three-dimensional object. Yeah, okay. So that's good enough for art class, right? So a solid three-dimensional object going on there. Okay, so what I want to do is I want to find that bounded region. I need to figure out the intersections, where I start, where I stop. If you're rotating about this y equal 1, what is perpendicular? Perpendicular would look like this. So that's definitely a dx slice for my rectangle. Okay. Where do they intersect? Well, that curve right there is y equals 2 minus x squared. So I set them equally to each other. So I have 2 minus x squared equals 1. We'll move the x squared over and move the 1 over. And so I get x equals plus or minus 1. So x equal 1 here, x equal minus 1 here. All right? So I'm summing my rectangles. I'm going to sum my rectangles from what? From -1 to 1. Okay? And then how do I find the volume of one of those discs? So how do I get the volume of one of those discs? Well, I need the radius. Well, what is the distance for some arbitrary x value from here to here? How do I get that distance? Well, that distance is actually equal to the top minus the bottom, right? So what is the top? The top is the curve 2 minus x squared, and the bottom is the line, the horizontal line, 1, top minus the bottom. So what is my arbitrary radius? Remember, it's pi r squared h. So the arbitrary radius r is 2 minus x squared minus 1. Okay, and the width is dx, that delta x there. And so this simplifies pi times 1 minus x squared squared dx. And so I'm going to sum all those rectangles. I'm summing all of the rectangles from -1 all the way to +1. Okay? So pi and then 1 minus x squared squared dx. Okay? So when you run through that math, and I challenge you to do so, multiply this out, distribute, factor the pi out, okay? And I think if I did this real quick, that's 1 minus 2x squared plus x to the 4th dx. Run through the integration, figure out the indefinite integral, evaluate f of b minus f of a, and you should get approximately 3.351. Okay, so just run through that, see what you get. Okay, just try it out, see what you can do with that. Okay. So really, I always think back to what is my basic shape that I'm trying to add up. Okay, and then how do I find that radius there when I'm thinking about the disc or the washer, right? And so I'm always thinking like top minus bottom. So you see, this problem ended up being different. Okay, it ended up being a very different problem because that distance from where we were rotating about changed from the x-axis to the line y equal to 1. Okay, so you got to be careful in how you set up the problem and then how you integrate. So I want to talk about just in general, just so I can drive this home for you. So if you're still kind of confused, maybe this will hopefully to clear it up for you. So for the disk method, all right, remember the disk is just that solid disk, right? How do we do the disk method? Well, the disk method says the volume is equal to pi times the integral from a to b of the function f of x all squared dx when we revolve around x-axis. Okay, when we revolve around the x-axis. So with a picture, because I know some of you guys like pictures, I know I like pictures. Some of y'all may like them, some of y'all may despise them. You know what, that's okay, because that's how life is. All right, so if you have some curve f of x, and so that's my f of x curve, and now I'm integrating from a to b, so that's kind of the cutoff there at that point to that point. So I'm trying to find the volume. So if I spin it around the x-axis, then that creates this shape kind of like this here. Okay. Don't you just love this art class that we're doing here? Like, Mr. Clark, can't you just finish this dang video? Okay, so that's what's going on there. So the 3D version of what's going on there. And so your height, that radius, any radius is found by taking the top minus the bottom. Well, the top is f of x and the bottom is 0. It's that y equals 0 for the x-axis, okay? It was different for this problem because the bottom was y equal to 1, so that's why I had to subtract the 1 to figure out that radius, okay? So if you're revolving about the x-axis, then this is your formula, okay, for finding the disk method, okay? If instead you're revolving about the y-axis, then the volume changes. It becomes integral from c to d of, instead of f of x, maybe it's some g of y function, okay, squared dy, delta y. That's whenever I revolve around y-axis. Remember, when you are doing these problems, your rectangles are perpendicular, okay? They're perpendicular. So if you're revolving about the x-axis, then you're forced to have that dx component going on, okay? If you're revolving about the y-axis, then you're going the exact opposite way, okay? So to draw the picture there, so say this is some function g of y, okay? And then I integrate from c up to d. Okay, so this kind of gives you the cutoff once again. So this is my little area piece here that I'm revolving about the y-axis. So I'm spinning it about the y-axis here. Okay. And so when I spin this about the y-axis, oh, that's ugly. All right, let me try that again. Okay. Doing my best here to give an accurate 3D representation of what's going on there. All right. So to be perpendicular here to the y-axis, I need rectangles that are dy oriented, okay? And then once again, the distance, it's for your dy, remember it's the right minus left scenario, okay? So the right minus left scenario gets you that distance here. So that's that g of y minus the x equals 0. So that's why it's just g of y, okay? And not g of y minus some number, okay? So this is a delta y differential there, okay? So hopefully that helps you out with the disk method. And really the washer method, all it is the disk method twice. So the washer method, okay, the volume is equal to, well, it's an integral from A to B of the big disk area squared minus the little disk area squared, okay, dx. And if you think about what the area is, well, it's pi r squared, right? So that area, that r, this is, I'm sorry, that's a capital R and a lowercase r, right? So I'm literally, let me rewrite this in the same form that I did above, okay? Squared here and then squared here. So this pi can factor out of both. And so I have pi factored out A to B of the big radius squared minus the little radius squared dx. Now this is for revolving about x-axis. Okay, so if I revolve it about the x-axis, this is the scenario, okay? This here is the outside circle area, which is the big one. And then this one here is the inside circle, which is small. Okay, inside circle radius, outside circle radius. Okay. So, and I think I drew this in a picture earlier, but I'm going to copy and paste this down here so I don't have to redo it again. But when you're talking about the disc and washer method, with the washer method, okay, the small radius is right here. The big radius is right there. Okay? So when you are using the disc / washer method, the rectangles are perpendicular to the revolving axis. Okay? So if I'm revolving about the x-axis, then if this is the x-axis and this is the y-axis, then my disc, my washers, are going to be perpendicular. Okay? So the way I remember it is perpendicular. It's silly, it's stupid, but I never forget it. Okay? And that's, usually how it goes. The dumber it is, the more chance you'll have of remembering it, right? That's why you'll never forget me. Okay, so let's do one example where I show you again how to do the revolving about the x-axis with a washer method. And then I think we'll finish this video, and then I'll have one more video that just does 2 more examples. Okay? So I want to find the volume of the solid bounded by the curves y equals 4 minus x squared and y equals 2 minus x, revolved about the x-axis. Okay? So I'm going to revolve about the x-axis. I need to first draw my graph. So I'm going to spin it about the x-axis. I know that. Okay? Y equal 4 minus x squared. Y equal 4 minus x squared. So it's a parabola. It's a negative parabola. It's shifted up 1, 2, 3, 4 units. Okay? And then it comes down like this. Crosses the x-axis at 2 and negative 2. Then I have y equal 2 minus x, so 2. So y equal mx plus b. How do I graph a line? So that's negative x plus 2. So first thing I do is I put a dot on the y-intercept, and then my slope is a negative 1. So I go down 1 over 1, down 1 over 1. So I see that my line is like this here. Okay, so I'm going to drag this through here. So I see I intersect in 2 places. To figure out where those intersect, I'm going to set them equal to each other. So 4 minus x squared equals 2 minus x. All right. I'm going to move the x squared over because I like to have my x squared terms positive. I'm going to move the negative 4, negative 4. So I have 0 equals negative 2 minus x plus x squared. So x squared minus x minus 2 factors, I believe, to x minus 2x plus 1. Right? Go to the factored video if you're having trouble with that. So x equals 2 and x equals negative 1 are my intercepts. So x equal negative 1 and x equal 2. So where is it bounded? It's bounded here. So I'm going to take that region and I'm going to rotate it about the x-axis here. So I'm going to spin it about the x-axis. So that's kind of a weird looking shape. I'll try my best to draw that. Then I have a cross section. Okay, and now I'm going to spin that. Oh, that's not right. Let me try that again. Okay, that's my best attempt. So it's like the middle has a cone punched out of it. Okay? So the middle has a cone punched out of it. So the whole object kind of looks like this. With that cone punched out of the middle. Alright, so that's the best 3D version that I can do. Okay, so that's gonna have to be good enough. Alright, so how do we do this? So it's definitely, when I look at this and I take one cross section in there, I see that I've got a cross section and it has a hole punched out of the middle, right? So I have a little r punched out, and then I have that big R that I need to calculate, okay? So my formula, remember, it's pi, integral from a to b, big R, big radius squared minus little radius squared dx, okay? So really the only thing I got to figure out is I got to figure out what is the distance from the axis I'm rotating to the little radius, and then what is the distance from the axis I'm rotating to the big radius. So remember, these are arbitrary x values that we're plugging in, right? So really all we need is the equation. So that distance from here to this little radius, well, for arbitrary x, what is it? It's y equals 2 minus x, right? So the little radius is 2 minus x. Okay, that was easy. And the big radius what is the big radius? The big radius is that distance from the x-axis, which is 0, up to this curve up here, the parabola, which I think was y equals what? 4 minus x squared. So that, for some arbitrary rectangle in there, that's going to be 4 minus x squared. 4 minus x squared in here. Okay? So now the last thing I have to do is I have to figure out where am I summing the rectangles up to. So my arbitrary rectangle is perpendicular. It's a dx. It's perpendicular to the axis I'm rotating about. Good. So I need to figure out, where do I start summing my rectangles? I start at x equal negative 1, and I add them all the way to x equal to positive 2. So I integrate, I sum, I add them up from negative 1 to 2. So now I've got to do some arithmetic or algebra, I guess, to simplify these here. You could do it over here. 4 minus x squared squared is 4 minus x squared written twice. That's 16 minus 8x squared plus x to the fourth. And then 2 minus x times 2 minus x, that's 4 minus, oh, that's 4x, I think. And then plus x squared. Okay, so that's 16 minus 8x squared plus x to the fourth minus parentheses 4 minus 4x plus x squared. People mess up because they forget to put their parentheses here, okay? Just a common mistake. If you simplify all that, you're going to get 12, and then that becomes a minus, so that's minus 9x squared, and then plus 4x, and then plus x to the fourth dx. And you can integrate that, and when you integrate all of that, you're going to end up with an answer of 108 pi over 5. I want you to try to do this. Integrate each term, and then do f of b minus f of a. Okay, and then multiply the whole thing by pi. All right? So see what you can do with that problem. That's a lot of algebra at the end for that f of b minus f of a after you do the calculus part of it for the integration. But I definitely think that it's doable. Hopefully this video explained the washer and disk method more to where you understand it. Now I didn't write out the washer method for revolving about the y-axis, but it's super easy. It's it's basically the same formula. I'll just do it real quick just so you'll have completed notes if if you're like that. It would be pi integral c to d of r, capital R of y, so the functions in terms of y squared, and then little r of y squared, and then dy. Okay, revolve about y-axis. Okay, so that's just, for symmetry for you. Volume. Okay. All right.